Now we're going to talk about the induced map, which is a map that is sort of automatically defined whenever you have a linear map from one place to another. So, and it kind of connects the gap between the quotient space and the thing that it's isomorphic to, like we saw in previous examples. So suppose we've got a linear map from V to W, and we take U to be the null space of this linear map. Then we are going to define the induced map from the quotient space V mod U into W by it's the thing that sends the equivalence class V plus U to where T would have sent V. Okay, and so you can always do that for any linear map. Now, why would you want to? Okay, well, that's a whole other conversation. And this is the content of Theorem 391. Okay, so this induced map is linear, injective, and it has the same range as the original T. Oh, whoops. As the original T. And the big kicker is that V mod U is isomorphic to the range of T tilde, which is the same as the range of T, so I'll just leave it without the tilde. Okay, now I'm not going to go through the steps of proving this theorem. What I want to do instead is look at this picture, and you'll see that we are back to the fundamental theorem of linear maps. So let's see what's going on in this guy. So let's see. So here I'm looking at something like the example in the previous clip. So it looks like this, think of this as R3, right? And we've got a linear map from R3 into R4. And over here, I'm going to take the z-axis as the null space of T. And then if we look at the quotient map corresponding to this particular space here, then what we see is that the resulting equivalence classes, well, it looks like I fix an xy coordinate in the xy plane, and then add in any vertical vector, so any element of U, the vertical subspace. And so the collection of all these equivalence classes looks like the collection of all these vertical lines right here. So each one of these vertical lines is an affine subspace, which is parallel to the original U that we started with. So there's a nice picture for you of what V mod U looks like. Now, how does that have to do anything with the current theorem? Oh, I guess I can fill in some detail over here. So this blue guy is the one we called Z in the previous clip, in the example where I did R3. And so here our vector space V, which is decomposes as the direct sum of Z and the null space of T. And then if we come over here to look at the induced map is going from the quotient space to the range of T. And wait a minute, I don't want that one. There we go. So here's where the induced map lives. And so what it's telling us is that V mod U is isomorphic to the range of T. And so you can see, sure enough, for every point over here in the, for every one of these sort of fibers in V mod U, they're indexed by the points of the XY plane, and they look like basically the set of the XY plane, and that's exactly what this is telling you. It is more or less. So there's gonna be a one-to-one correspondence between the points over there and the points over here in the blue plane. And so what else do we have? So we have that the range of T is equal to the range of T tilde. They're both mapping to the blue plane. And we also have that the blue plane gets mapped to the other blue plane on the other side by T. So this is the range of T over here, the blue guy. And so this is the isomorphism that between Z and the range of T. And so what this tells you is if you take your linear map T and you just look at the restriction of it to the XY plane, so the complement in the direct sum, so just this guy here, then it sets up an isomorphism between these guys. Okay, and now that last part, so this isomorphism here, this is not asserted by the theorem. I'm just telling you that on the side. We'll get to that again later when we cycle back to the fundamental theorem yet again. For the meantime, I'll just point out that this space over here on the right looks like the range of T direct sum D, where D is some mysterious object to be revealed in section 3F, or sorry, chapter 3F. And if we come back over to the equation for the decomposition that we had of V here, you can see that the dimension of V, so just applying the dimension on both sides, is dimension of Z plus dimension of null T, which is the dimension of the range of T plus the dimension of the null space of T. So that's how it ties back in with the rank nullity theorem.